calculus. Does that sound exciting? A little bit. So we're going to look at differentiation as our first unit. Calculus is based on an idea of a limit, and a limit is something that you can get really, really close to. Now there's two types of calculus. We do both of them. We do differential calculus first, and then we do integral calculus afterwards. Integral calculus, which was sort of discovered first or talked about first, is looking at areas under curves, and we can trace it all the way back to Archimedes, and that's about 250 BC for that idea. Differential calculus with derivatives, that's looking at rates of change, different kind of slopes of tangent lines, and it's discovered in the 17th century, and it's usually associated to two people, Newton and Leibniz. They both discovered it independently, but not necessarily in the same year. Okay, but nowadays that would make a big difference, right? If you invented the first electric car that was economical and really efficient, you would be associated with that. If someone else found it 3 years later, you'd be like, yeah, that's way out of date. But back then, they didn't have the internet or anything like that. And so both of these gentlemen discovered calculus in their own notation, in their own ways, separately, independently of each other. So you're not saying, well, I discovered it first and he stole my ideas. In fact, during that time, they didn't really share ideas very much. Academics was very different then. You sort of hoarded your knowledge. If you discovered something, you didn't necessarily let other people know. So there's some interesting stories back then of knowledge sharing and how things worked. An average rate of change. Okay? So, for example, if I were to drive from here to Brandon, it's 200 kilometers, and it takes me 2 hours. Well, my average speed is 100 kilometers per hour. Now, if my average speed is 100 kilometers per hour from now here to Brandon, that doesn't mean I'm driving 100 kilometers per hour the whole trip, right? There's certain, like in Winnipeg here, before I leave the city, I can't just put cruise control 100 kilometers, just go through every stoplight and zip past everybody. I'll get I'd be going way over the speed limit. But if my average is 100 kilometers per hour, you can also say, oh, Mr. JR, you were probably speeding somewhere along the way. Because, well, I guess the highway is 110. So maybe I was okay. So that's about average rate of change. So we've got this situation here, 3 points, and we can calculate average rates of change from one point to the next. So if your x values go from 1 to 3, okay, and your rate of change or your slope is your change in your y values divided by your change in your x values. So going from 1 to 3, my change in my x values is 2. My change in my y values going from 6 to 12 is 6. So my average rate of change is 3. Now if we added, to make this more interesting, if we say this is time in seconds and distance in kilometers, yes, that would make it more interesting. Definitely. Okay? What this part A says, you are traveling on average 3 kilometers per second. That would be your average speed over those parts. In fact, the slope is perfectly straight. The slope of that line is 3. You're traveling at a constant speed each time through that at 3 kilometers per second. But if you would go from 1 to 4, add a bracket here, add a point. Okay, from 1 to 4, change in y over change in x, your x has changed 3 when you go from 1 to 4, but your y hasn't changed at all. Okay? So if we're looking at your average rate of change, you haven't moved. Sounds pretty boring, in fact. You went, in 3 seconds you haven't moved, according to your average rate of speed. If you look at what actually has happened, right? You went 3 kilometers per second. I don't know what would happen to your body if you actually traveled that fast. And then you traveled back to that spot that you were and ended up in the same place 3 seconds later. But in reality, what's happened here, you've gone 12 kilometers in 3 seconds. But you happen to be back to where you started from. I really don't think your body would be much of anything if you traveled that fast and that far in 3 seconds. But your average rate of change is 0 from 1 to 6. And if we went from 1 to 5, well, now your change in x is 4 seconds, and your change in y, you've gone from 6 down to 0, gives us -3 over 2, -1.5. Well, the negative in this situation is probably giving you some direction, right? 3 kilometers forward would be positive, 3 kilometers backwards would be negative. So the negative here is giving us some sort of sense of direction. Now your slope, you've already learned way back from grade 10. If you take 2 points on a graph and figure out the change in y over the change in x, that will be your slope. And calculating your slope between any 2 points, well, that's just your average rate of change. So I think for you, this next bullet is actually missing. But it says here, notice finding the average rate of change between the 2 points on a curve or on a function is the same as finding the slope of that straight line joining those 2 points. Now, calculus is based on a concept of a limit, and you have already seen some limits, or the idea of a limit, if you go back to geometric sequences. So for example, if I start 16 paces away from the wall, or 16 tiles away from the wall, and I always walk half the distance that I am away from the wall. It's going to show up with this sequence right here. Would you agree that the first time I would walk 8, and then I'd walk 4, and then I'd walk 2, and then 1, and then a half, and then a quarter, and then a 1/8, and a 1/16, and a 32nd, 64th, 1/20. Wow. You could keep going. Would I ever hit the wall? No. But if I did it forever, I would say that I could get arbitrarily close to the wall. In fact, I would say the limit, if I kept going forever, is that I would reach the wall or get as close to the wall as possible. Because every time you say you can't get closer to that, well, I'll walk halfway closer. Now I'm closer again. So that's the idea of a limit. And so we say as that sequence gets larger and larger, the term gets closer and closer to 0. Because if I did it 1,000 times, I'd basically be almost right at the wall, and then like the little tiny bit, go half of that distance. and half of that distance, and half of that distance. And so the terms eventually approach 0. And you've learned that if you add up an infinite geometric sequence, like if you added this one up, the total distance I would have walked is 16 at infinity. Basically saying at infinity you'd reach the wall, or be so close to it that it's basically going to be 16 in the end. Now, the actual term is never equal to 0, but we say that it is so close to 0 that it's arbitrarily close. And that's the idea of a limit. We say the limit of un equals 0 as n approaches infinity. Right? Try adding up all the terms. We already talked about that would add up to 16. That's your, remember this, sum to infinity, u1 over 1 minus r. Back in grade 11, you had t1 over 1 minus r. So as n approaches infinity, the sum approaches 16. So we would say the limit of Sn is 16 as n approaches infinity. Now we call sequences that come or approach a certain number convergent, because as each term increases, the sequence gets closer and closer to a value, and that value is called a limit. Here is what the notation looks like in this example. The limit as n goes to infinity, that's how you would read that first part, of the sequence un is equal to 0. And we could write the limit of the sum to look like that. So sequences that are convergent have a limit. Sequences that are not convergent are called divergent, and they don't have a limit. So there's the first 3 terms in a new sequence. 0.2, 0.22, 0.2222. What would the next one be? The fourth term would be? And so now you imagine doing this to infinity. What number does this get closer and closer to? Can you write that number as a fraction? So we have to imagine, if we kept going, what number is it getting closer and closer to? Tell me as a decimal. Once we've got it as a decimal, then tell me as a fraction. Does it get closer? Does it ever become 0.24? So then if we say 0.3, then it would have to somewhere get to 0.24 before it gets to 0.25. But someone's saying it doesn't get to 0.24. So then the question, well, does it ever get to 0.23? Well, if it got to 0.23, somewhere along the line it would have to get to 0.224, 5, and it doesn't get to that anywhere. Does it make sense that this gets closer to 0.2 repeated? I mean, if you had infinite amount of steps, you'd have an infinite amount of 2's, which would be 0.2 repeated. But if you stopped at any point saying, oh, I just want to check where are we at on the 1 billionth one. Oh, that's 0.22222. No, I won't go through them all. But you'd have a billion 2's. Would that be closer to this? Yes. But would it be there yet? No. But eventually, that's the number you get closest to. Does anybody know what that is as a fraction? 2/9. Oh. Have I ever gotten off topic with you on fractions over 9? Maybe? Like, you know that 1/9 is 0.1 repeated? 2/9 is 0.2 repeated? 3/9 is 0.3 repeated? Anybody know what 9/9 is? It's 1. You can't write it as 0.9 repeated? Which is bigger? Oh, I am getting off topic. What's bigger, 0.9 repeated or 1? 1? They're actually the same number. This is like a little bit of mind-blowing, okay? So yeah, I'm getting off topic a little bit because it's interesting. Two numbers, if they're different, you can always put a number in between them, no matter how close they are together. Would you agree? There is no number in between 0.9 repeated and 1. So using that, they're the same. Now, we could prove this in a couple of ways. I mean, one was just looking at the pattern. 1/9 is 0.1 repeated, 2/9 is 0.2 repeated, 3/9 is 0.3 repeated. So therefore, 9/9 has to be 0.9 repeated. But that doesn't seem very logically based. So sometimes people do, well, we could add fractions, 1/3 plus 1/3 plus 1/3. If you add them, you get 1, right? If you change these to decimals, the nice thing about this, would you ever have to carry a 1? No. So if you added the decimals, that would happen. That might convince you a little bit more that 1 is equal to 0.9 repeated. Or perhaps we do it with algebra. See, let x equal 0.9 repeated. Okay? So we'll start with that. Then if I multiply both sides by 10, then 10x is equal to 9.9, right? I just moved the decimal place over 1, but the 9's would all continue. Then on the left side, I'm going to subtract x. And on the right side, I'm going to subtract the number, because x is equal to 0.9 repeated. What's 10x minus x? 9x. What would happen here? You just get 9. Divide both sides by 9. And what's x equal to? 1. But what did I start with? X was equal to 0.9 repeated. X is equal to 1. They're the same. Okay. Sorry, I got a little off topic. I hope that was fun. Limits of functions. So we say the limit as x approaches a number, f of x, is equal to some value. So it means that if you get arbitrarily close to c, whatever that number is, from either side, you could figure out what the limit is. And again, you've done this a little bit already, and we'll see some examples as we go along. Sometimes, okay, sometimes the limit is so easy you just plug in the number. For example, the limit as x goes to 2 of x squared. So if we graph x squared, there it is, would you agree that you have the point 2, 4 on x squared? So the question that's really happening when they say the limit as x goes to 2, they say as I get closer and closer and closer and closer to 2 from this direction, and as I get closer and closer to 2 from that direction, what does my y value get really close to? 4. Some limits are super easy, because really all you had to do was plug in 2. If you plug in 2, you get 4. And if we type in these values into our calculator, we're going to find out that, I don't know what I'm making up numbers, but, ooh, this one I should be able to do. 3.24, 3.61, I don't know if I'm guessing here, but it's getting closer to the 4. And then as soon as you go over 2, it might be 4.01, 4.001, 4.41, 4.84. But the idea right here, as you get close to 2, the numbers seem to indicate that we're getting closer to 4. How would I ask you to evaluate a limit like this one? I'm going to tell you, evaluating a limit like this one, you just have to plug the number in. Super easy. But sometimes we run into issues. And this is the most typical kind of limit question. What's the limit as x gets close to 1? What's the problem with just plugging it in? The last one, we could just plug it in and get the answer, no problem. This one, if we plug in 1, what does our denominator become? 0. Are you allowed to divide by 0? No. But we graphed these last year. Do you remember graphing x squared minus 1 over x minus 1 in grade 12 pre-calculus? What did you do first? Yes, I remember graphing them, but I don't remember what I did first. Well, top I can factor. Why is factoring nice here? Oh, this cancels out. Now is this starting to trigger something? What does that mean when they cancel out? It's not an asymptote, right? X equals 1 is an open circle. It's a hole in your graph, or if you want to use the proper fancy math words, a point of discontinuity. So after that x minus 1 cancels out, this just becomes x plus 1. Well, x plus 1 is an easy thing to graph. It's a straight line, right, with a y-intercept of 1 and a slope of 1. But it has a hole in it. And it has a hole where? At 1, 2. How do I know it's at comma 2? Because I can plug 1 into the simplified version. On my line, I should have the point 1, 2, but now I have a hole in my graph. And so when we're talking about the limit, as you go from the left-hand side and approach x equals 1, and you go from the right-hand side and approach x equals 1, from the graph, we can say that the limit is equal to 2. What we'll do algebraically for limits is very similar to what we did algebraically to graph them, right? Once it was simplified, you could graph it. So with our limit, we can't plug in 1 yet. But if I factor I can simplify, and then once it's simplified, can you see now you could plug in 1 without a non-permissible value? Plugging in 1 there makes it equal to 2. So often what we'll do is we'll try to simplify our equation in order to evaluate our limit. And we can see it from the graph because we graphed these one before. As you go from the left or from the right, as x gets close to 1, your y value gets close to 2. And so we would say the limit as x goes to 1 is equal to 2. Again, you could type each of those values into your calculator and see the same result, that it's getting closer and closer to 2. In fact, here, this one I can do the mental math. This was 1.8, 1.9, 1.99, 1.999, 2.001, 2.01, 2.1, 2.2. And this is what we're looking for. When it gets close to 1, what number does it get close to? It gets close to 2. Another type of function that you probably haven't seen for a while is something called a piecewise function. A piecewise function is when the equation is written in 2 different pieces. It's one equation for some of the domain and another equation for the rest of the domain. So in this one, it says whenever x is bigger than or equal to 0, f of x is 1. So I'm going to graph that in blue. And whenever x is less than 0, it's equal to -1. And here would be an open circle because it says less than 0, but not less than or equal to 0. And now the question is, what happens as x gets close to 0? What's the value of this function? And this is where things get a little bit interesting, because when x is 0, what is this function equal to? +1. So sometimes students are tempted to say the limit as x goes to 0, because I can plug it in, should be +1. But in this case, I'm going to introduce you to some new notation. The limit as x goes to 0 from the left-hand side. So we write a little tiny negative above the 0. That means you're coming to 0 from the left. That's like this. I'm going to 0 from the left. What number am I getting closer to? -1. But when I go from the right side, coming from the right going towards 0, we would say the limit from the right side is +1. In fact, we could fill in the chart here. It's -1, -1, -1, -1, +1, +1, +1, +1. This is what we're looking for what is the limit as it gets close to 0. And if it doesn't approach the same value from the left as it approaches from the right, then we say the limit does not exist. So we can write that out. Limit, this is how you could write it, x goes to 0 of f of x does not exist. It's not possible. So even though you can plug in 0 and get a value, the limit doesn't exist. So we talked earlier about an average rate of change. And I drove from here to Brandon and was averaging 100 kilometers per hour. That's an average rate of change. An instantaneous rate of change is if you phoned me while I was driving and you said, Mr. JR, look at your speedometer right now. What does it say? And I say 115 kilometers per hour. That's how much I'm traveling in that instant. That's my instantaneous rate of change. Sometimes I'm going to be stopped at a stoplight. Then I would say my speedometer says 0. That's the instantaneous rate of change at that moment. Okay? So a tangent line, that cuts a curve at one point. So remember, if you phone me, there's a tangent line touching that curve at that one point. That's like phoning me and say, what is your instantaneous, what speed are you going right now? If you took 2 points and joined them, that's called a secant line. Now these definitions aren't quite perfectly accurate, but you drew tangent lines to circles back in grade 9. Do you remember doing that? And so if you had a circle, a tangent line always touches only at one point. This would be a secant line, touching at 2 points. Okay? But we have to be careful with that definition a little bit, because in the green curve that I just drew, if I drew a line straight up and down, that would cut that curve only at one point, but that wouldn't be considered a tangent line. Does that make sense? The tangent line at this point would be like this, still touching only at that one point, but that would be a better indicator of what the average rate of change is. Because the idea, okay, don't want to get too far into it, but can you see if you took 2 points really close together, right? That would be the secant line. And if I moved the points closer and closer and closer together, it would get closer and closer to the tangent line, not closer to the one that's going up and down. So as those points get closer and closer and closer, or as we take the limit, as that distance gets smaller and smaller and smaller to 0, the limit becomes the tangent line. Okay? So you phone me. How fast are you going right now? 150 kilometers later. Okay? 10 seconds later. How fast are you going right now? 117 kilometers an hour. So then you say, oh, so your average speed is 116 kilometers an hour in 10 seconds. Yes, because you asked me 10 seconds apart. Okay? But if you ask me 1 second apart, wouldn't it be really close to what I'm traveling instantaneously? Yes. Your average between, what now? What now? It'd be a really annoying phone call all the way to Brandon every second. How fast are you going now? How fast are you going now? Ooh. You just put it on cruise. I'm going to be on cruise for the next half an hour. Don't phone me. Hang up. So this is the idea that I was just talking about. If you drew a secant line, I'm going to see if I can, I'll see if I can find an applet on the internet for this. But if you drew a secant line through those, you could find the slope of those. Okay? That is an average rate of change. But as these 2 points, as B1 becomes closer, if you kept moving B1 along here, along here, along here, until it was really, really close to A1, and then you connected the 2 points, the secant line becomes a tangent line. And the gradient of that tangent line is your instantaneous rate of change. The question that you're going to have, here we have the parabola, y equals x squared plus 1. Pick a point on there. Pick an x value. Not too big. 32? No. You're going to make me square 32 in my head? 3. I like that. 3. Would you agree that you have the point 3, 10? You could draw, right? 3 squared, 9 plus 1, 10. Yeah, okay. You could draw a tangent line. Wow. As best as you can, straight as possible. Now we're going to need to learn how to use that applet and that a secant line becomes a tangent line, because you're going to need to find the equation of that line. First of all, what's the slope of that line? How do I know it's 6? That's a good question. How do I know that the equation of this line is y equals 6x minus 8? How do I use calculus to help me figure all of those things out? That's what we're going, right? That's what, like, when I showed you the app, right? This becomes this. Now we've got some fiddling to do with the algebra. How does that algebra help me with stuff? How do I use that to figure out, when I picked a random point on this last one, how did I know that that slope at that random point of the tangent would be 6? How would I know that my equation then becomes y equals 6x minus 8? Okay. So, if we chose the vertex, go back to the app that we did. I'm going to get right to the vertex. Does it make sense that your tangent line is horizontal at the vertex? Yes. And so as we drag this here, it also becomes closer and closer to horizontal. Perfect. So according to our definition was wrong, there would be 2 tangent lines at the vertex. We could do a vertical line or a horizontal one, but only the horizontal one is true for the tangent. So our definition that we started with needs to be improved. Here's an improvement. A line that touches a curve at one point and whose gradient of the line is equal to the gradient of that curve at that point. So now our algebra that needs to come in. How do we figure out what's happening? So we take 2 points. Okay? And in this notation, here's my x point, here's my y point. Okay? And then I'm going to add some value of h. Would you agree that this x point is now x plus h? And this y point would be plugging in x plus h into that function. What happens when I take point B and drag it closer and closer to A? What happens to h? H gets closer and closer to 0. So the algebra can be represented as a limit. First of all, would you agree that the slope of AB is just rise over run? Rise over run f of x plus h minus f of x over x plus h minus x, which just becomes x. Just using the notation that we have here, this is the slope of our secant line. And then here's the concept of the limit. If we let h go to 0, then the secant line is going to turn into the tangent line. And we would write our tangent line as a limit as h goes to 0 of our secant line. This is the definition of the derivative. All the derivative is, that fancy calculus word that's been a nebulous for so long, all a derivative is the slope of a tangent line. It's not that exciting, sorry. And we calculate the slope of a tangent line by taking a secant line and making that h value go closer and closer to 0. So in our equation, which we had before, f of x equals x squared plus 1, I would have to plug all of the information into here and evaluate the limit to figure it out. The problem with the limit right now is you're dividing by 0. So you're going to have to do some algebra to make that dividing by 0 go away. And then you can evaluate any limit from there. Okay, so this formula, it's known as Newton's quotient, or the first principles of the derivative, or the definition of the derivative. And using Newton's quotient to find the derivative, you can find a gradient function, or a function. Gradient is another word for slope. And so you can find a function that can find slopes of tangent lines. Again, calculus is about finding slopes of tangent lines. Right now, you should feel somewhat like, I don't know, doesn't sound that, like, calculus is this big thing and it's just slopes of tangent lines. It seems like it's a little bit of a letdown. It is really quite exciting what we're all going to be able to do with it. But yes, initially, totally feel that letdown like that's all it is. But we're going to be able to use that idea to apply it in so many situations that it's going to be, in my opinion, really awesome. Yes? Yes. F prime of x. An inverse notation has little minus 1. Okay? And this isn't an f1 of x. Okay? Oops. There we go. Oh, there we go. It's a little bit of an angle. It's like an apostrophe, but not like one of those fat apostrophes with a little circle thing. It's like just a regular slash apostrophe. Okay. So you can have either f prime of x or y prime if you're using y notation, or f of x. These first two tend to be more aligned with Newton's notation. Okay? Leibniz used this notation, dy by dx, which stood for change in y over change in x. So we will work with both notations all the way through. I think we have time to do one example just to get an idea. So 3x squared plus 4. First of all, okay? First of all, what's happening here is you've got a parabola moved up 4 units. It's narrower because of the 3x squared. There's our graph. Okay? Would you agree that on this point you would have 1, 7? I'm going to tell you, before I do all this math, that if you drew a tangent at 1, 7, its slope is equal to 6. We're now going to figure out how the algebra shows us this. So this question says use Newton's quotient. So we need to use the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, just double check that I didn't change your notation at all. Perfect. So what do is we have to use our knowledge of functions, because we're given what f of x is. F of x, well, this is a new notation, the f double dot x. This means the same thing. I try to introduce as many different IB notations as I can find in my examples, so that if you see them on an exam, you're not scared by them, or if you see them in a textbook. Okay? Well, what is f of x plus h? That would mean you'd plug in x plus h for x, right? You agree? And then I'm supposed to do minus f of x. Well, f of x is just 3x squared plus 4, all divided by h. So f of x was given to us. That's 3x squared plus 4. F of x plus h, that means you have to plug in an x plus h wherever there was an x. That's what function notation means. Okay? Can we evaluate this limit right now? Can you plug in 0 for h? No. You're not allowed to plug in 0 for h because you would divide by 0. So our job is to do some algebra and hopefully cancel out this h on the bottom. Okay? So what can I do algebraically? You have to keep writing limit h equals 0 all the time. Well, I can expand this. That'll be x squared plus 2xh plus h squared plus 4, and distribute this negative, minus 3x squared minus 4. And then I can distribute this 3. So then I would have limit, as h goes to 0, of 3x squared plus 6xh plus h squared plus 4 minus 3x squared minus 4 Can you see that the minus 4 and the 4 would cancel out? Can you see that a 3x squared and the minus 3x squared would cancel out? This is still all over h. What does that leave on the top? That leaves a 6xh plus h squared. Can you simplify that with an h on the bottom? Okay? Yes. Okay? If you can simplify it right away, that's fine. Some people like to factor out an h on the top. Can you see that I could factor out an h on the top of the two things that are left? Oh, sorry, it should. I missed that 3. And then that would still be 3h. Perfect. Can you see you could factor out the h? And then these h's would simplify. And now you can apply your limit. What happens if I plug in 0 for h now? What do I get? I just get 6x. In fact, here I'll put equal signs all along here. I'll use Leibniz notation right from the beginning and write, this is our derivative. So our derivative is equal to 6x. View the entire screen right now. Okay? In other words, the slope of the tangent line is equal to 6x for every value of x. What value of x did I have at 1, 7? My x value is 1. If you plug 1 into this equation, what do you get? 6. If you picked another point, say you picked the point over here at -2, 16. Somewhere there you're going to have that as your tangent line. If you plug in -2 into this equation, I can tell you that the slope of this one is -12. So using Newton's definition, you plug things in and then you have to use the algebra until that h cancels out so you can evaluate your limit. Once you evaluate your limit, the derivative is a gradient function. In other words, it's a function to find the slope of every single tangent line wherever they are on that graph. Yes? How did I know the slope was 6? Because you're going to be mad at me because I'm going to make you do this. Okay? How long did this take? Maybe 5 minutes? Okay? And then I'm going to show you a shortcut that can save you 4 minutes and 58 seconds off of every 5-minute question. Wow. But I'm not allowed to show you the shortcut yet.